Hi, so here we are again, it's Mrs. Allen, and we're looking at 1.2 limits involving infinity for AP Calculus AB. And I first have a warm-up for you, so take a minute, pause your video, solve both number 1 and number 2, and we'll review it. Okay, now that you had a chance to look at these questions, then for the first one, you would have said the limit as x approaches 3. If you put in x equal to 3, you find out that you have 0 over 0 in indeterminate form. The limit of the numerator is 0 and the limit of the denominator is 0. So if you factor the numerator, you get x plus 2 times x plus 3, or x minus 3. Cancel the x minus 3's, and then you're able to take the limit as x approaches 3 of x plus 2, which turns out to be just 3 plus 2, which is 5. So your answer is C. Okay, and hopefully that worked out for you. For the next one, find the limit as x approaches 2, and that would be from the right. So when you read that little plus sign there, make sure you understand that. So if we look at a number line with number 2 right in the middle, that would be coming in from the right, or the left would be the top. So on this branch, on the right side, we have 5 over x plus 1, where on the left side, we've got 3x plus 1. So we definitely want to use this 5x plus 1. So all we have to do is say the limit, well, it's going to approach a value when x is greater than or equal to 2. It's going to be this function. So we're just going to 5 over 2 plus 1, which is 5/3, and our answer is A. So I hope both of those worked out for you. So with the piecewise functions, sometimes they're a little daunting, but once you get a hold of them, they're not really that bad. So here we go. Limits at infinity. The objectives we want to, or what we're going to be working with here, is the squeeze theorem for limits at infinity. And we've already worked with those at a particular value, say C, the limit as x approaches C. Now we're going to look at the limit as x approaches infinity or negative infinity. We have asymptotic and unbounded behavior of functions, such as those at vertical asymptotes, and then end behavior of functions where you might have, as x approaches infinity, it might approach a finite value at a horizontal asymptote. So limits can be used to describe the behavior of functions for numbers large in absolute value. What happens when x becomes like 1,000 or 10,000 or 1 million? So that addresses the issue of horizontal asymptotes. So the line y is equal to b is a horizontal asymptote of the graph of the function y is equal to f of x if either, let me make it a little bit smaller, fit everything on there, if either the limit as x approaches infinity of f of x is equal to b, or the limit as x approaches negative infinity of f of x is equal to b also. So if you kind of look at this graph that you have here, I have the asymptotes are in green, the line y is equal to b, and you can kind of see that as the function approaches negative infinity on the left, you can kind of see it go into the b, and then as the function comes up, as it gets bigger and bigger, and as the x values approach infinity, then our y values approach b also. So kind of hover. A horizontal asymptote is a horizontal line to which a graph tends to. It gets really chummy with. So in the same thing here, happens here, the limit as x approaches negative infinity, or the limit as x approaches positive infinity, is going to be y equals b. In this case, it would be y is equal to 0 here, where b is equal to 0, but nonetheless, the graph tends to that horizontal line. Okay, and that's because your function value, if you look at the last one, your function value would approach 0 no matter as x gets really, really big, whereas in the first example, the function approaches the value of b as your x values get really big. So let's take a look at the first one here, example 1, limits at infinity and horizontal asymptotes. So use a graph and tables to find the limit as x approaches infinity, the limit as x approaches negative infinity, and then identify all horizontal asymptotes. So the function f of x is equal to x plus 1 over x. So the first thing I would do a lot of times, just to clarify what I was looking at, is pull out my graphing calculator and of course go to y1 and put this function in. So y1. and see what it looks like. Notice there are two branches, not just one. So we've got, it looks like we have a vertical asymptote there. And you guys are familiar with some of this language that we're talking about because you're recognizing that x can't be 0. So x equals 0 is the vertical asymptote. And then when I look at it, it looks, just from a first glance, it looks like the function kind of levels out here at y is equal to 1. So I'm going to put that y equal 1 here. I could be wrong about that, but let's just see. So what you're going to do is you're going to trace on your calculator and just put in some values. So if you notice, you put in the value of 4. If you put in x is equal to 4, you get 4 plus 1, or 5 over 4. So it's 1.25, 5/4, 1.25. And so you're just above 1. Now, as you continue to trace and you go out, you notice if you hit the arrow on your cursor pad, it'll start to scroll. So you want to go out there and see how far you get. It looks like you get very, very close to 1. So 1 is going to be my choice right now. Can I put that in here? Let me get a better color. So I'm going to say that it's 1. Okay, so the limit as x approaches infinity is 1. And I'm going to say the same thing because it looks like it does the same thing over here, but let's just try 1 point. If I go 1, 2, 3, 4, do I want to say 4, or let's say -3? Let's say -3 right here. So if I put -3 on here, -3 plus 1, -3 plus 1 is -2. -2 over -3 is 2/3. So you kind of see where your value is getting bigger. You know, you're coming up towards 1. It goes from 0 here somewhere to 2/3. So let's handle this like this. Let's say, well, I think it's approaching 1 also on that side, right? So we want a kind of a surefire way to say this. So I know that when we have this discussion in Algebra 2 classes, like the degree of the polynomial is 5, the degree of the polynomial is 4, the end behavior of the graph is this, as x approaches infinity, what happens to y? That's a huge discussion, and sometimes students will feel like, I don't even know why I'm doing this. But you see, the leading term is the powerhouse, okay? The leading term of the numerator is x, right? X. It's just x to the first power. And in the denominator, the same way. So what we really can do, and I want you to bank on this, is we can take the leading power, I'm going to put a 1 there just for the accent, 1x over, and in the bottom, the leading power is also that. When I divide this, what do you get? What do you notice you get? Just 1, right? So the horizontal asymptote then, the horizontal asymptote is y is equal to 1. Okay, because after some time, and we'll talk about it in some other examples, after some very short amount of time, that little plus 1 in the numerator means nothing. It's not going to change the value by hardly anything, and we're going to approach the value of 1. Okay, so take a look at that if you need to pause it and rewind. Okay, now let's look at the second one. Revisiting the squeezing theorem, we have the limit as x approaches infinity of cosine x over x. We want to handle it graphically, and you can kind of see what it's doing. It looks like it's wrapping around the x-axis, and I kind of highlighted that function in red there. As x goes to positive infinity, what's happening to y? It looks like it's going to 0, right? Well, we don't want to just say that. We want to have some kind of a graphical, yes, we have that. I can also look at a table of values. I'm going to hold off on the table of values because you guys can do that in your graphing calculator. Remember that last week what we did, it was we said, okay, let's take the range of the sign, and it goes from -1 to 1. We're going to do the same thing with cosine. So with cosine, it goes from -1 to 1. And notice that this argument I want to take the limit of is cosine x over x. So I'm going to build that in a new inequality. I'm going to say the second step is that I'm going to take this, and I'm going to say -1 is less than or equal to cosine x is less than or equal to 1. And then I'm going to divide each part of this by x. Okay? So I now have a new inequality. I have a new inequality. And what I'm going to do is I'm going to take the limit as x approaches infinity. I don't think I'm going to have enough room here. I'm going to make this a little bit smaller. I love when that happens. Okay, so the limit as x approaches infinity, why does that happen? I'm going to have to investigate that. Okay, so Okay, well, I'm going to try it one more time here. Okay, third time is a charm here. Let's make that, put that x back into place. Okay, now I'm going to insert my functions. So I have negative, we'll do it like this. Negative 1 over x is less than or equal to cosine x over x. And scooch this out a little bit. Okay, is less than or equal to the limit of 1 over x. Okay, so now I know that the limit as x approaches infinity of negative 1 over x is going to be 0. Negative 1 over infinity is just 0. So that's going to be 0 is less than or equal to the limit as x approaches infinity of cosine x over x. And recall that at this point, let me digress just a little bit. We can't do this because if we put infinity in here, we would have cosine infinity over infinity. We don't know what that is because cosine oscillates. It bounces back and forth between 1, 0, negative 1, 0, 1, 0, negative 1, 0, and all the numbers in between. So it oscillates, so we can't really say what the limit of infinity is, but we know that we can capture it between two known values, negative 1 and 1. So, and if you look at the end point here, the limit as x approaches infinity of 1 over x, then we've got 0 there as well because 1 over infinity is 0. Therefore, we can conclude then that the limit as x approaches infinity of cosine x over x is equal to 0 by the squeezing theorem. I have sandwiched my limit between two known limits here, the limit of 1 over x on the right and the limit of negative 1 over x on the left. Okay, so there we have it. There it is for that one. So all of your properties from limits also hold true. The limit as x approaches a finite value such as c includes all these rules, and the same thing is true with the limit as x approaches plus or minus infinity. So we have the sum rule, the difference rule, the product rule, the constant multiple rule, the quotient rule, and the power rule. So what I would do is I would categorize these and understand how you're using them. I wouldn't say that I would say them every time I'm using them, but make sure that you're aware that all of those can be applied. So now we have infinite limits as x approaches a, and we have vertical asymptotes. The line x equal to a is a vertical asymptote of the graph of the function y is equal to f of x if either one of these two limits is true. So either the limit as x approaches a of f of x is equal to plus or minus infinity, or the limit as x approaches a from the left. I forgot to say right. This little plus sign, the limit as x approaches a for the right of f of x is equal to plus or minus infinity, or the same thing, the limit as x approaches a from the left. So you can kind of see here on the left-hand side for the first one, here's the n. So we've got the limit as x approaches a from the left-hand side, and here we have the limit as x approaches a from the right-hand side, where x is equal to a. So on the left, it goes to positive infinity on this particular graph, and on the right, it goes to negative infinity, it being the function. So, and then for our graphs here, as x approaches a1 from the left, we use that little superscript, the function is going up, so it's going to positive infinity. Let me highlight that as I was doing. And so the limit as x approaches a sub 1 from the left is going to negative infinity, here positive infinity, and then negative infinity again. So you can kind of see the behavior of the graphs. If it's a vertical asymptote, this must be true. The limit must go to positive or negative infinity. Okay, so infinity, quite a big deal here. Okay, so now example 3 talks about vertical asymptotes. So if we want to find the vertical asymptotes of a graph of f of x and describe the behavior of f of x to the right and left of each vertical asymptote, first thing I'm going to do is take a look at it and say, well, I know it has to do with where the function is undefined. So first I'm going to look at this and say there are no common factors between the numerator and the denominator, so I'm going to just set the denominator equal to 0, and then I'm going to say 2 plus x, 2 minus x, I'm going to go ahead and factor it, set it equal to 0, and then I'm going to say where x is equal to plus or minus 2. So you can see that I have them marked on the graph, x is equal to 2 and negative 2. So then looking at this, If I evaluate the numbers here as I'm approaching x is equal to -2 from the left, it looks like the graph is going to negative infinity. Again, put this in your graphing calculator as you're trying to evaluate this. It makes so much sense. It's the best thing since sliced bread. It gives you the picture of what you're looking at in terms of the limit. So the limit as x approaches -2 from the left-hand side would, of course, be negative infinity then. Negative infinity, so you're headed down here. The limit as x approaches -2 from the right-hand side. Here's the right-hand side of -2. It looks like you're going to positive infinity. Now, we don't always put the plus sign there. I'm putting it there now. Then we have the limit as x approaches 2 from the left. 2 from the left is right here. So it looks like it's going to positive infinity. And then the limit as x approaches 2 from the right-hand side. It looks like it's going to negative infinity. So that's the behavior of the graph of the function 8 over 4 minus x squared. So example 4 for the end behavior of graphs. If we want to find the end behavior of the graph for this model, a really simple tool can be used for this. If you think as x gets really big, what are you going to do? So you can say, well, the limit as x approaches infinity of, I'm going to write the whole thing out, 3x squared minus 2x plus 5 over 4x squared plus 7. And what I want you to do is take a second and look at the numerator and denominator, and I want you to say if there is a boss term to be had, which one is it? And I want you to highlight it in the numerator and then go to the denominator. So if I look at the numerator, I see that, it's not working out very well. So I'm just going to put a circle around it. So if I put a circle around this term, I'm going to say that's the boss term because it's the most powerful term if I put an x, and especially a big x. And then in the denominator, it's going to be the 4x squared, right? So I can say that this expression is not going to be too affected in the numerator by a minus 2x and then a plus 5. Those are kind of dinky terms compared to a 3x squared, for crying out loud. And then at the bottom, the plus 7 isn't going to mean too much. So what I can do is I can say this is going to be equal to the limit as x approaches infinity of 3x squared over 4x squared. That's going to simplify then to the x squareds are going to cancel, and it simplifies to 3/4. So it's equal to 3/4. Let me get a brighter color here. So we're going to say the limit, maybe let's put the answer up in the box up here because we're getting close to the end. So the limit gives us the end behavior as x approaches infinity is going to be equal to the limit as x approaches negative infinity. So the graph, we'll write a little sentence out for this. So the graph will tend to the horizontal asymptote y is equal to 3/4 as x goes to plus or minus infinity, and that should be enough. So a couple things to remember about polynomials, so end behavior of graphs. When we're looking at facts, the leading term or the leading degree, if I look at a real quick example of this, and I say if I have f of x is equal to 4x cubed minus 2x squared plus x plus 17, sounds like a lucky number, and I have g of x is equal to 4x cubed. As I'll run out of room. As x goes to plus or minus infinity, these two things, f of x is just going to go to g of x. In other words, there's going to be very, very little difference after some time. You consider when x is equal to 1,000, okay? So we often compare functions only because f is a little more complicated than is g. We like functions like g, okay? So if we're dealing with rational functions, what we can do is we can say, all right, well, let's give an example with this. If the numerator degree is equal to the denominator degree, then we're going to take the leading coefficients. I think it's always easier if you have an example to work with. And I'm just going to use a linear one. So if I have this example, then I can highlight here, there's the leading term. The degree is the numerator. If the degrees of the numerator and denominator are equal, I can then do what I did in that last example and just say that the horizontal asymptote, H period, A period, is just going to be equal to 2/3, or the coefficient of the leading terms, right? So kind of convenient to have. I'm just going to leave that there, and it's not letting me. Okay, and then okay. Now, if the numerator, so there's your horizontal asymptote, easy to get, right? So the -1 and the +5 are irrelevant after a really short time. However, if the numerator degree is less than the denominator degree, so if I get a function such as this, if I say f of x is equal to, say 8 over x minus 1, something like that. Well, then the degree of the numerator is, the numerator degree is 0. The degree of the denominator degree is 1. So whenever this happens, the horizontal asymptote is then y is equal to 0. So because think of it like this, the horizontal asymptote is the quotient value after when x gets really, really big, right? So think about this, 8 over a really big number minus 1. Right? It's going to go to 0. So think about that. Now, the last case that I didn't go over, when the numerator is larger than the denominator degree, then you don't have a horizontal asymptote. Sometimes you have a slant asymptote if the difference is 1, but I'll talk about that in class. So here's your exit ticket. If you'd like to pause this, try it out, and which of the following lines is the horizontal asymptote for that particular function. Okay, now that you had some time pausing the video, now I'm going to highlight the highest degree term in the numerator and the denominator. You have to be careful because they're not always written in what we call descending order. So you can see that if I took the 3x cubed over 2x cubed and simplified it, I would get 3/2 for an answer. So now the answer here is not A. You got to watch out for that because there's no x in it. It would just be simply y is equal to 3/2. Okay, I'm going to end this video. I'll come back and do the examples for the rest of 1.2. More examples. Someone asked for more, please, and you're going to get it. I'll talk to you later. Bye.